Right now, sitting inside your gaming PC, or maybe the computer rendering the very video you're watching, is one of the most sophisticated objects ever manufactured by human hands. It's not magic, but when you understand what's actually happening inside it, it's gonna feel pretty close. Here's a number: 82 trillion. That's the number of mathematical operations a modern RTX 4090 graphics card performs every single second. To put that in perspective, if every single person alive on Earth right now did one calculation per second, without stopping, without sleeping, 24 hours a day, it would still take over 10,000 Earths of people to match what this one chip does in the time it takes you to blink. And today, we're gonna go inside it. Not just the hardware, the actual logic, the architecture. The reason this same technology that renders your video games is now rewriting the rules of artificial intelligence. Let's go. Your computer has two main processors: the CPU, the central processing unit, and the GPU, the graphics processing unit. And most people assume they basically do the same job. They don't. Think of it this way. The CPU is a Formula One car, blazing fast, extraordinarily smart, built to handle complex decisions at incredible speed. It's running your operating system, your browser, your apps, managing every device connected to your machine all at once. It's a genius that can do anything. But there's a problem. A Formula One car has one driver. The GPU is something else entirely. A modern GPU, like NVIDIA's Ada Lovelace architecture, has 16,384 shader cores. That's over 16,000 tiny processors working simultaneously. Each one isn't as fast or as smart as a CPU core, but they don't need to be, because the work of rendering graphics or training an AI isn't about solving one hard problem fast. It's about solving millions of simple problems all at once. And that distinction, that single insight, is what makes GPUs one of the most important inventions of the last 50 years. Let's go inside. A modern GPU die, the actual silicon chip, is manufactured using a process so small it defies imagination. NVIDIA's latest chips are built on a 4-nanometer process. A single nanometer is 1/1000th of a meter. The width of a human hair is roughly 80,000 nanometers. These transistors are so small that quantum effects, the weird, uncertain physics of subatomic particles, start becoming actual engineering problems. The chip is organized like a hierarchy. At the top level, you have graphics processing clusters, or GPCs. Inside each GPC are multiple streaming multiprocessors, or SMs. And inside each SM, you find the actual workers: CUDA cores, Tensor Cores, and ray tracing cores. Think of it like a corporation. The GPC is a division, the SM is a department, the individual cores are the employees. And just like a well-run company, everyone has a very specific job. CUDA cores, named after NVIDIA's parallel computing platform, are the generalists. They do the fundamental math. Multiply two numbers, add them together, output the result. They do this billions of times per second. They're the reason games render at all. Tensor cores are specialists. They handle matrix multiplication, which sounds boring until you realize that every AI model ever trained is essentially doing enormous amounts of matrix multiplication. These cores are the reason your graphics card can also power machine learning. One tensor core can perform hundreds of operations simultaneously in a single clock cycle, operating on entire grids of numbers at once. And then there are ray tracing cores, hardware units built specifically to simulate how light behaves in the real world, tracing individual rays of light from a virtual sun, bouncing them off surfaces, tracking how they scatter, absorb, reflect. This is why modern games can have reflections that look photographically real. It's physics simulated in real time. Here's the thing most people miss when they talk about GPU performance. The cores are almost never the bottleneck. The memory is. Imagine hiring 10,000 workers to build a house. They're fast, efficient, ready to go, but there's only one truck delivering materials. The workers will sit idle most of the time, waiting. That's the memory bandwidth problem, and solving it is one of the most active battlegrounds in chip design right now. Modern graphics cards use GDDR7 memory, the 7th generation of graphics double data rate RAM. GDDR7 moves to a 3-voltage signaling system called PAM3, which allows it to transmit more data per signal than its predecessor. A high-end card with GDDR7 can achieve memory bandwidth exceeding 1.8 terabytes per second. That means in the time it takes to say the word "one," your GPU can transfer a stack of data larger than most people's entire hard drives. But even that isn't enough for AI. That's where HBM, high bandwidth memory, enters the picture. Instead of placing memory chips beside the GPU, HBM stacks them vertically, like floors of a building, directly next to the processor. The communication between the stack and the chip happens through microscopic vertical tunnels called through-silicon vias, or TSVs. The result is a memory connection so wide it can transfer multiple terabytes per second. The NVIDIA H100, the chip at the center of today's AI revolution, uses HBM3 with 3.35 terabytes of bandwidth per second. That's roughly 50 times more than what your gaming PC's RAM can do. Here's the part that still amazes me every time I think about it. The chip inside your gaming computer, the one designed to render dragons and explosions and sunsets at 4K 120 frames per second, is the same category of chip training the AI models that are reshaping medicine, science, and how we communicate. How? Because training an AI neural network and rendering a video game are, at their mathematical core, the same type of problem. Both require performing the same operation, multiply, then add, across mountains of data, in parallel, as fast as physically possible. When you ask an AI to write something, or generate an image, or diagnose a disease from a medical scan, underneath all of it, billions of matrix multiplications are happening. Numbers being multiplied, results being summed, over and over and over. This is called a dot product, and the tensor cores inside a modern GPU can execute millions of dot products simultaneously. NVIDIA's Blackwell architecture, announced in 2024, pushed this further still. The GB200 chip connects multiple dies together and achieves over a quadrillion AI operations per second, 1 petaflop of AI inference performance, in a single chip. The engineering required to achieve that involves not just the silicon, but the packaging, how chips are physically connected to each other, how heat is removed, how power is distributed across hundreds of watts without destroying the chip. It's one of the most complex manufacturing challenges in human history. Let's talk about how these things are made, because it's genuinely one of the most extraordinary industrial processes ever devised. Every GPU starts as a wafer of silicon, a thin disk cut from a crystal grown from sand. That wafer is then patterned using extreme ultraviolet lithography, EUV, a technology that uses light with a wavelength of just 13.5 nanometers generated by firing a laser at tiny tin droplets moving at 200 miles per hour, creating plasma that emits the UV light. This light is then focused through mirrors so smooth that if they were scaled to the size of Earth, their imperfections would be smaller than a marble. This process repeats dozens of times on the same wafer, layer after layer of circuitry stacked atop each other, precisely aligned to within fractions of a nanometer. No wafer is perfect. Defects happen, particles land, patterns misalign, so chip designers build in redundancy, extra cores that can replace defective ones. This is why an RTX 4090 and an RTX 4080 are sometimes made from the same chip. The 4090 has all its cores working, the 4080 had a few disabled after testing. Same silicon, different bin. Billions of transistors, made by machines that themselves took decades to invent, shipped into products that sit on a desk and run games or help scientists fold proteins or generate art. That's what's inside your graphics card. The next time your computer renders a frame, or a chatbot answers your question, or a scientist uses AI to discover a new drug, somewhere a chip made of sand and light and human ingenuity is performing trillions of calculations per second to make it happen. And now, you know exactly how. If this blew your mind, consider this. We haven't even talked about what comes next. Photonic chips, optical computing, neuromorphic processors that work more like a human brain than a calculator. The story isn't over. It's barely started.